In the last part of the lecture, I'm going to discuss gravitational potential energy and power. Earlier, I stated that there are two types of energy associated with the mechanical motion of objects: kinetic energy and also gravitational potential energy. I'm going to tie gravitational potential energy and kinetic energy through the principle of conservation of mechanical energy. Let's look at the following situation. An object is tossed up in the air. Let's say a ball with some mass is tossed vertically up with some initial velocity v initial. It is going to rise to a certain height above the point of release, which I'm going to call initial position. And it's going to slow down as it's going up, and eventually it will stop at the highest point of the trajectory. At the highest point, the ball is going to have a different velocity, v final, which will be 0 since the ball is instantaneously at rest. And this position of the ball I'm going to call final position. At the initial position, the ball has kinetic energy. Kinetic energy initial, which we know is calculated as mass times velocity squared divided by 2. At the final position, the ball has kinetic energy final, which is equal to 0 because the ball is instantaneously at rest. But we also know that energy is neither destroyed nor created, so that means that this initial kinetic energy that decreased as the ball went up in the air and became 0 couldn't be just vanishing. It doesn't vanish into nothing. It must be converting into something else. Well, it is converting into gravitational potential energy. Gravitational potential energy. So now let's discuss what gravitational potential energy is. Gravitational potential energy, or GPE, is the energy associated with vertical distance from a predefined 0 level. Gravitational potential energy is calculated as the product of the mass of an object that is moving vertically up or down times the gravitational acceleration g times the distance h from the predetermined 0 level. G is 9.8 meters per second squared, the gravitational acceleration of Earth, and then h is a vertical distance from a predetermined 0 reference level. So what is that predetermined 0 reference level? The predetermined 0 reference level would be any reference level that you want to measure the vertical distance from. For example, you may want to measure vertical distance of a moving object from the ground. So as the object is moving up or down, you just measure the distance from the ground, and the ground is your 0 reference level. At that reference level, the gravitational potential energy is 0. Above or below that level, the gravitational potential energy is not 0. For example, the drawing that I made right here, I can take my 0 reference level to be at the release point of the ball. So the gravitational potential energy here is 0. And as the ball is moving away or up from this level, the gravitational potential energy increases, the kinetic energy decreases. At that height above the release point, the ball contains gravitational potential energy, which is equal to mgh, and that gravitational potential energy is not zero, but at the release point it is zero, just because I decided that this will be my zero reference level. For our purposes in this course, the zero reference level will be usually the ground. So let's say take the ground level to be the zero reference level. So we are going to measure vertical distances from the ground level when we calculate gravitational potential energy. So I define gravitational potential energy. What are the units in which gravitational potential energy is measured? Well, in the example that I showed here, the kinetic energy became gravitational potential energy. We know that the kinetic energy is measured in joules, and so since gravitational potential energy is just another kind of energy, the units for gravitational potential energy will be also joules. This example, with the ball going up in the air and the kinetic energy converting completely into gravitational potential energy, is an example of the principle of conservation of mechanical energy. The principle of conservation of mechanical energy simply states that the mechanical energy of an object is constant at all times. This is only true if there are no resistive forces acting on that object. So this is true if there are no resistive forces acting on the object. What are some examples of resistive forces? Well, that would be force of friction, and air resistance. Those are the two more common resistive forces. So force of friction and air resistance. So for any object that is in motion and is not a subject of the force of friction or air resistance, the mechanical energy of that object is constant at all times. It is conserved. Okay, so now what exactly is the mechanical energy of an object? So the mechanical energy, which we abbreviate as ME, is equal to the sum of the kinetic energy of the object and the gravitational potential energy of the object. And so the statement of the principle of conservation of mechanical energy simply says that the mechanical energy, which is the sum of those two energies, is equal to a constant. Presented explicitly as a formula, the mechanical energy is equal to the kinetic energy mv squared over 2 plus the gravitational potential energy mgh, and this is equal to a constant. The principle of conservation of mechanical energy can be used to solve certain types of problems where an object is in motion and its kinetic and gravitational potential energies change as the object is moving, but because of the absence of resistive forces, the sum of those two energies remains constant. An example of such type of motion would be an object that is released to fall from a certain height above ground. A 500 gram ball was dropped from a height of 2 meters above ground. What is the velocity of the ball as it hits the ground? Let's do this example. To solve this problem and answer the question, we need to use the principle of conservation of mechanical energy. So conservation of mechanical energy. Okay, so let's see what we know. We know the mass, which is 500 grams. Notice that the units are not the correct units for the calculation, so this must be converted into kilograms. So 500 grams is 0.5 kilograms. We also know the height above ground, h, which is 2 meters. And of course, not stated in the problem, but we know is the gravitational acceleration, which is 9.8 meters per second squared. What we are looking for is the velocity with which the ball hits the ground. So let's sketch the problem. So this is the ground, and the ball starts somewhere here above ground at a height h, which is equal to 2 meters. So at the starting position, initial position, the mechanical energy of the ball, mechanical energy initial, is equal to kinetic energy initial plus gravitational potential energy initial. And then the ball falls down towards the ground, and as it hits the ground, this is the final position. The mechanical energy final will be equal to kinetic energy final plus gravitational potential energy final. And we know from the principle of conservation of mechanical energy that the two mechanical energies, mechanical energy initial and mechanical energy final, are equal. That means that kinetic energy initial plus gravitational potential energy initial is equal to kinetic energy final plus gravitational potential energy final. Kinetic energy initial is equal to 0 because initially the ball is at rest. Gravitational potential energy initial is simply mgh. This will be equal to kinetic energy final, which is equal to mv squared divided by 2. And gravitational potential energy final will be equal to 0 because I'm going to select the ground. Remember, we talked about it on the previous slides. The ground to be my 0 level. So at the 0 reference level, the gravitational potential energy is 0. So gravitational potential energy final is 0. Okay. So then what we have left to work with is that mgh is equal to mv squared divided by 2. Since I have the mass on both sides, that will cancel out. And so from here we have that gh is equal to v squared divided by 2. And I'm going to rearrange the terms and solve for the velocity. So v squared is equal to 2 times gh. And from here, finally, v is equal to square root of 2 times gh. Now I can substitute the values that I know for the mass. Actually, I don't need the mass, for the height and gravitational acceleration. And that's going to give me v is equal to square root of 2 times 9.8 meters per second squared times 2 meters. And the result of this is 6.3 meters per second. Notice something very interesting. So this ball has some mass, 500 grams. However, The final result for the velocity is independent on the mass. The formula here does not contain mass, which means that for an object of any mass, to calculate the velocity with which it's going to hit your zero reference level, let's say the ground, only depends on the gravitational acceleration, which close to the surface of the Earth is constant, and the height above ground. That's all. So the mass is irrelevant. Now, I want you to keep something in mind. In this particular example, the initial kinetic energy was 0, and then the final gravitational potential energy was 0. However, anywhere in between the two positions, the initial and final positions, I may be asked to calculate, let's say, the velocity. That means that I need to keep in mind that between the initial and final positions, the kinetic energy will be changing. So it starts at 0, but then it starts to increase. The gravitational potential energy starts at its maximum value, but then it starts to decrease. And so as the gravitational potential energy decreases, the kinetic energy increases. So somewhere in between the two positions, I have a sum of kinetic energy which is non-zero and gravitational potential energy which is non-zero. But the sum of the two is constant. So anywhere between those positions, including them, the sum of kinetic and potential energy is constant. The individual energies values will be different. Okay. An important quantity related to energy is power. Power is defined as the change of energy with time. Power is the change of energy with time. For power, we use the symbol P, capital P. Do not confuse it with momentum, which was lowercase p. And this is equal to the change in energy with time. We know that the units for energy are joules, the units for time are seconds, and so the units for power are joules per second. However, as you may have heard, there is a different unit that is used for power, and that is the watt. Now be careful not to confuse the units of watts with the abbreviation for work, W. We also know from the work energy theorem that the change in energy was equal to the work done by a force. So an alternative definition of power would be that the power is equal to the work done divided by the time for which the work was done. So the work done per unit time. This definition can also be interpreted as the efficiency with which work was done. Because imagine a person is lifting, let's say, 500 kilograms of bricks from ground level to 1.5 meters above ground. So in the process, they are applying force to lift the bricks, and therefore that means that they are doing work. Now, we don't know how long it took that person to move those bricks from ground level to above ground. Did it take them 1 hour, 1 day, 1 month? We don't know. But if we can calculate the power that was developed in the process of moving those bricks, which means work done per unit time, then we can essentially calculate the efficiency with which that work was done. You can imagine that the efficiency would be different if all that work was done in 1 hour versus 1 day versus 1 year. Here is an example of the application of the concept of power. A car traveling at 27 meters per second experiences resistive forces of 300 newtons due to air resistance and friction of the tires with the road. How much power must the car's engine produce to compensate for the resistive forces? So here we are just looking for the power that the engine must produce to compensate for the forces and not to move the car after that. Okay, so first we must calculate the change in energy that is result of the work done by the resistive forces. So the change in energy, delta E, will be equal to the work done by the resistive forces. So this is force times distance. That will be 300 newtons. That is the resistive forces acting together. The distance traveled would be 27 meters. So 300 newtons times 27 meters. That gives us 8,100 joules. To calculate the power that needs to be developed by the engine to counter the effect of those resistive forces, we are going to divide that change in energy by the time it takes for that change to happen. So this would be 1 second. And so we have delta E divided by delta T. That will be 8,100 joules divided by 1 second. So this is 8,100 watts. So the engine must produce power of 8,100 watts to overcome just the resistive forces due to air resistance and the friction with the road. And then everything else will go towards the car actually moving on the road with some velocity, acceleration, and so on and so forth. And with this, I'm going to conclude the lecture on energy.